Tonight, we're going to talk about one of the strangest discoveries in modern astronomy. A telescope that has only been fully operational for a few years has found objects that no one expected. Tiny, compact, intensely red points of light scattered across the deepest images of the early universe. They sit in a period of cosmic history where, according to every model we have built over the past 50 years, they simply should not exist in the form we observe them. They are, by every rule we know, impossible. And by the end of tonight, you are going to understand what these objects are, why they sent shockwaves through the field of astrophysics, and why the most compelling answer turned out to be a theoretical prediction that had been sitting mostly unread in a published paper for 16 years, waiting for a telescope powerful enough to prove it right. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The James Webb Space Telescope launched on the 25th of December, 2021. It had been in development for more than 2 decades, a project that began in the late 1990s as the planned successor to the Hubble Space Telescope, was originally expected to cost around $500 million and ended up costing nearly $10 billion. The delays and cost overruns were not the result of mismanagement alone. They were the result of genuine engineering difficulty. Webb is the most complex space observatory ever built by human hands. Its primary mirror, made up of 18 hexagonal gold-coated beryllium segments, stretches 6.5 meters across. That mirror could not be launched as a single rigid structure. It was too large for any existing rocket fairing. It had to fold up, origami style, fit inside the rocket, and then unfold in deep space, one segment at a time, over the weeks following launch. The same was true of the sunshield, a 5-layer, tennis court-sized membrane designed to block the heat and light of the sun so that the telescope's instruments could be kept cold enough to detect faint infrared signals. Each layer of the sunshield had to fold up for launch and then deploy in sequence once the telescope was in space. Hundreds of mechanical release points, each of which had to work flawlessly in the vacuum of deep space, where no repair mission was possible. The margin for error was essentially zero. The launch finally came, and it was flawless. The deployment that followed was tense engineers and scientists watching each step, aware that a single failure in any of hundreds of systems would end the mission. But it worked. By July of 2022, the telescope was fully commissioned and returning scientific images. Images that immediately surpassed everything that had come before them. The reason Webb could do this, the reason it can peer deeper into the universe and further back into cosmic time than any previous instrument, comes down to one fundamental physical fact. It was built to see the universe in infrared light. The universe is expanding. It has been expanding since the Big Bang, and that expansion carries a consequence for every photon traveling through it. As light travels through expanding space, the space itself stretches. The wavelength of the light stretches along with it. Radiation that began its journey at ultraviolet wavelengths, emitted by a hot young star in the early universe, has its wavelength elongated as it crosses the billions of light-years of expanding space between its source and us. By the time that light arrives at our detectors, it may have shifted from ultraviolet into the visible range, or from visible into the near-infrared. Light from the most distant objects, the objects at the highest redshifts, emitting radiation when the universe was only a few 100 million years old, has been stretched so far that it arrives in the mid-infrared range. Hubble was designed primarily for optical and ultraviolet observation, with some near-infrared capability added in later years through instrument upgrades. It was not built for the wavelengths where the earliest universe glows. Webb was. Its detectors, its instruments, and its entire thermal design were oriented toward the infrared. The sunshield that keeps the telescope cold is not a luxury. It is a necessity. An infrared telescope operates by detecting tiny amounts of heat radiating from extremely distant objects. If the telescope itself were warm, its own thermal emission would overwhelm the faint signals from the early cosmos. Webb operates at a temperature of around -233 degrees Celsius, specifically to keep its own thermal noise low enough that the instruments can detect the signals they are built to find. That design paid off immediately in the first deep field images. Scattered across those images were small, intensely red, compact points of light. They were not subtle once you knew what to look for. They stood out against the background of other galaxies and stars. Because of their distinctive color and their compactness, dots of deep red in images where most objects were blue, white, or multicolored diffuse structures. They appeared in every deep field image, Webb returned. Not occasionally. Every time. In some of the deepest fields, they were present in numbers that surprised everyone who reviewed the data. They were extremely compact, unresolved, even at Webb's angular resolution, meaning the telescope could not distinguish their spatial extent on the sky. They appeared as points, like stars, rather than the extended, diffuse structures you would expect from a galaxy at any stage of its development. They were red in a way that placed their peak emission in the near-infrared, consistent with objects at high redshift whose light had been stretched during its long journey across expanding space. And they were concentrated at redshifts, corresponding to the era roughly 500 million to 1 billion years after the Big Bang, the period when the universe was completing its transition from the Dark Ages into the age of galaxies and stars. These objects had no established category. They did not fit the morphological description of any known type of galaxy. They were too compact and too bright at those distances to be individual stars. They showed features in their spectra that were inconsistent with standard active galactic nuclei as they had been understood for decades. They were something new, something outside the established inventory of cosmic structures. That is genuinely rare in modern astronomy. The sky has been surveyed so extensively over the past century that finding a fundamentally new category of object requires either a telescope with capabilities that previous instruments lacked, or access to a regime of the universe that had simply been invisible before. Webb provided both. In early 2024, an astronomer named Geordie Matthey and his colleagues published a formal catalogue of the objects in the Astrophysical Journal. The paper documented their properties, measured their redshifts, analyzed their spectra, and gave them a name: little red dots. The name was deliberately informal. In the technical literature, they also appeared under the more descriptive label of broadline H-alpha emitters, referring to a specific spectroscopic feature they shared. But the informal name stuck because it was short, it was memorable, and it was accurate. They were small. They were red. No one knew what they were. By the time the catalogue was published, more than 1,000 had been identified in Webb's data. That number has continued to grow with each new survey. In some of the deepest fields, approximately 1 in every 100 objects at the relevant redshifts turns out to be a little red dot. That is not an anomaly or an oddity. That is a population, a substantial, consistent population of objects that the entire field of astronomy had never seen before. sitting in a part of the universe and a period of cosmic time that had been, until Webb, essentially invisible. To understand why the little red dots are such a profound problem, you need to understand what the early universe is supposed to look like. Cosmology, the science of the origin, structure, and evolution of the universe as a whole, is built on a framework developed over roughly a century of observation and theoretical work. It is called the Standard Cosmological Model, sometimes abbreviated as lambda CDM, a reference to the two main ingredients beyond ordinary matter and radiation that the model requires. The lambda refers to the cosmological constant, Einstein's term, for the energy of empty space that is now thought to drive the accelerating expansion of the universe. The CDM refers to cold, dark matter, the mysterious form of matter that does not emit or absorb light, but that nevertheless gravitates, and that appears to make up the majority of the universe's matter content. Together with ordinary baryonic matter and radiation, these ingredients produce a framework that has been tested against observations at every scale and every cosmic epoch accessible to our instruments, and that has consistently held up. At the foundation of this framework is a detailed picture of how the cosmos evolved from a hot, dense initial state to the structured universe we observe today. In the very first fractions of a second after the Big Bang, the universe was unimaginably hot and dense. In the first few minutes, temperatures fell to the point where protons and neutrons could combine into the first atomic nuclei, mostly hydrogen and helium, with trace amounts of deuterium, helium-3, and a small fraction of lithium. This process, Big Bang nucleosynthesis, produced the raw material from which all subsequent structure in the universe would eventually be assembled. For the next 380,000 years, the universe remained too hot for electrons to bind to atomic nuclei. It was a plasma, a hot, opaque sea of charged particles. Photons scattered constantly off free electrons and could not travel any meaningful distance without being absorbed and re-emitted. The universe was opaque to its own radiation. Then, as it continued to cool, electrons and protons combined to form neutral hydrogen atoms for the first time. The plasma cleared. Photons could suddenly travel freely through space, unimpeded, in all directions. The radiation released at that moment has been traveling ever since, cooling as the universe has expanded around it. We observe it today as the cosmic microwave background, a faint, nearly uniform glow of microwave radiation coming from every direction in the sky. It is the oldest light in the universe, a snapshot of the cosmos at an age of roughly 380,000 years. It has been mapped in extraordinary detail by space observatories, including COBE, WMAP, and the Planck satellite. The tiny temperature fluctuations, imprinted on the cosmic microwave background variations of roughly 1 part in 100,000, from place to place, reflect the density fluctuations in the early plasma. Those fluctuations were the seeds of all the structure that would later form. After recombination, the universe entered what astronomers call the cosmic dark ages. There were no stars. There were no galaxies. There were no sources of light of any kind other than the fading remnant of the Big Bang itself. The universe was filled with cold, neutral hydrogen gas and dark matter, both slowly being pulled together by gravity into the first dense concentrations of matter. Those tiny density fluctuations from the early universe grew over time under the influence of gravity. Slightly denser regions pulled in surrounding material, growing denser still. Less dense regions lost mass to their surroundings and emptied out. Over hundreds of millions of years, this process transformed the near-uniform early universe into an increasingly structured cosmos, with filaments and nodes of matter forming a cosmic web, and the spaces between them becoming the vast voids that make up most of the observable universe's volume. Then, around 200 million years after the Big Bang, the precise timing is still being refined. The first stars ignited. Gas in the densest regions had collapsed far enough that temperatures and pressures in the cores were sufficient for nuclear fusion to begin. The cosmic dark ages ended. For the first time since the Big Bang, the universe had internal light sources. These first stars, population, 3 stars, were fundamentally different from the stars we observe around us today. They formed from gas that contained only hydrogen, helium, and a trace of lithium. No carbon, no oxygen, no iron, no silicon. Without heavy elements, the gas could not cool as efficiently as modern interstellar gas does. And the stars that formed from it were likely enormous, possibly hundreds of times the mass of our Sun. They burned with extraordinary brightness and were short-lived. Within a few million years, they exhausted their fuel and ended their lives in violent explosions, seeding the surrounding gas with the heavy elements forged in their cores. Each successive generation of stars was born from gas enriched by the generations before. The universe's chemistry grew progressively richer. From those first stars, the cosmos began building up the elements that would make rocky planets, oceans, and eventually living things possible. From that point forward, the universe assembled structure, first individual stars, then small proto-galaxies gathering around dense concentrations of dark matter, then larger structures growing through mergers and the accretion of surrounding gas. The process is hierarchical. Small things form first. Larger structures grow from the accumulation of smaller ones over cosmic time. This picture is not merely theoretical. It is backed by decades of observations, computer simulations, measurements of the large-scale distribution of galaxies, and the detailed pattern of fluctuations on the cosmic microwave background. It is one of the most thoroughly tested frameworks in all of science. The era where the little red dots live 500 million to 1 billion years after the Big Bang falls squarely in the early stages of that hierarchical assembly process. Galaxies, at that age, should be young. They should be relatively small. They should be assembling their stellar mass gradually through a combination of internal star formation and mergers with other small structures. The universe has simply not had enough time to build anything much more massive than a few % of the Milky Way's stellar mass. The models that predict this are not vague. Galaxy formation simulations, some of the most computationally intensive projects in all of astrophysics, running on the world's most powerful supercomputers, are quite specific about what the galaxy population should look like at those redshifts. Faint and irregular. Blue, indicating ongoing but modest star formation. Relatively extended in their structure, and not yet very massive. What the little red dots appear to be is the opposite of every one of those predictions. The first quantitative measurements came with an immediate sense that something was fundamentally wrong. When astronomers tried to estimate the stellar masses of the little red dots using their observed brightness, they returned numbers that broke every formation model built over the previous half-century. A galaxy's brightness is proportional to the number of stars it contains, and from the brightness, you can infer the stellar mass if you make reasonable assumptions about the types of stars present. The masses came back far too high. Some of the little red dots appeared to contain stellar masses comparable to the Milky Way, a galaxy that has been accumulating mass for roughly 13 billion years. Finding anything comparable in objects only 500 million years old was not a minor deviation from the models. It was a factor of 10 or more beyond what the standard framework permitted. A team at Penn State gave the objects an unofficial name: universe breakers. The name was not hyperbole. It reflected a genuine assessment of what the data appeared to show. If these objects genuinely contained the masses their brightness implied, the cosmological models that had been built, tested, and refined over 5 decades of observational astronomy were in serious trouble. But the mass problem was only the beginning. The spectra of the little red dots, the detailed breakdown of their light by wavelength, were equally unsettling, and in a more complex way. To appreciate why, it helps to understand what a spectrum actually tells you, and why astronomers treat spectroscopy as one of the most powerful tools they have. Every element in the universe interacts with light in a specific and characteristic way. The electrons bound to an atom can only exist in certain discrete energy states defined by the laws of quantum mechanics. When an electron jumps from a higher energy state to a lower one, it emits a photon with a specific energy and therefore a specific wavelength. When an atom absorbs a photon, it must be a photon with exactly the right energy to cause a transition between allowed states. These transitions are fixed by physics and do not vary. Hydrogen always absorbs and emits at the same set of wavelengths, whether the hydrogen is in our Sun, in a galaxy 10 billion light-years away, or in a laboratory on Earth. Helium has a different set. Oxygen, carbon, calcium, iron. Each element has its own unique spectral fingerprint. A spectrum is therefore an extraordinarily information-rich measurement. From the spectrum of a distant object, you can determine its composition, its temperature, the density of its gas, the velocity of that gas relative to Earth, and, through the systematic redshift of all the spectral lines together, how far away the object is and how long ago the light was emitted. The spectra of the little red dots showed a distinctive and troubling shape that astronomers had rarely seen anywhere. In the ultraviolet part of the spectrum, the light was relatively bright. Then it dropped sharply over a very narrow wavelength range. Then it rose again in the red and optical. The overall shape was like a pronounced V, a steep cliff on the ultraviolet side and a rising slope on the red side. The edge of that cliff occurred at a specific wavelength, 364.6 nanometers in the rest frame of the object. This is the wavelength of the Balmer break. The Balmer break is produced by hydrogen, specifically by hydrogen atoms in their lowest energy state, absorbing photons that are energetic enough to ionize them to knock their electrons completely free. Photons with wavelengths shorter than 364.6 nanometers have enough energy to do this. Photons with longer wavelengths do not. The result is that a cloud of neutral hydrogen gas is essentially opaque to light below that wavelength and relatively transparent above it. An object surrounded by or embedded in a substantial amount of neutral hydrogen therefore shows a sharp drop in its spectrum right at that wavelength, a clear edge. The presence of a strong Balmer break carries a secondary meaning in galaxy science. In a galaxy with a population of old, evolved stars, stars that are billions of years old and have long since left the hot, blue main sequence, the light output is dominated by cooler, redder stars that are in advanced stages of their stellar lives. These older stellar populations naturally produce spectra with strong Balmer breaks because the light from the hot cores of the galaxy has been largely absorbed before it can escape. So, a strong Balmer break typically signals an evolved, mature stellar population, the kind you find in old, well-established galaxies that have been forming stars for billions of years. The little red dots had Balmer breaks among the strongest and sharpest ever measured at those redshifts, much sharper than theorists expected to find in objects from that era of cosmic history. And that created a direct and inescapable contradiction. A very strong Balmer break implies a galaxy old enough to have developed an evolved stellar population. But the universe at the redshifts where these objects live was not old enough to have produced such populations. The universe itself was less than 1 billion years old when this light was emitted. There was not enough time for galaxies to have accumulated the kind of evolved stellar populations that produce breaks that sharp. The spectrum was saying two things simultaneously, and those two things were physically incompatible. The first hypothesis offered to resolve the contradiction was the starburst galaxy model. A starburst galaxy is a galaxy undergoing an extreme and temporary episode of elevated star formation, usually triggered by an interaction or merger with another galaxy. Starbursts are well observed and well understood. When two galaxies come close to each other, or collide, the gravitational interaction can funnel large quantities of cold gas into the central regions of one or both galaxies. Gas that was previously spread across a diffuse disk gets compressed into a relatively small volume. When the compression is sufficient, gravity overwhelms the internal pressure of the gas clouds and they collapse into new stars. The result is a star formation rate that can exceed normal rates by factors of 100, 1,000, or even more in extreme cases. The Milky Way forms roughly 1 to 3 new stars per year in its current quiet state. An extreme starburst can form thousands of solar masses of new stars every year. Starburst galaxies have been studied extensively at lower redshifts and are recognized by a set of distinctive observational signatures. They are compact in their star-forming regions. They are bright, because the many young massive stars produce enormous luminosity. They are surrounded by dust, produced by the deaths of the first generation of massive stars, and that dust reddens the emerging light by preferential